For lesson 2.7, we'll be using the slopes of secant lines at a single point of a function to create a pattern that shows the slope of the tangent line for that same point. This is a really important lesson because the slope of a tangent line represents an instantaneous rate of change on a graph, specifically on a curve. This is one of the big things that we've been trying to figure out for this unit, so big deal lesson here. To refresh your memory, an instantaneous rate of change is the rate of change at a single point on a graph or a function. When we think of rate of change, we're thinking about it as a slope because we don't really have any context here, it's just a graph. So what we're looking for is the slope at a single point of a function, something that we're not normally able to do. Our secant lines will illustrate this point. A secant line is a linear line that goes through 2 points of a graph, and it's used to find a rough estimate of the slope at one of the 2 points that you're crossing through. However, the closer that those 2 points are together, the more accurate the slope at the point you are trying to find will be. So here you can see if I was trying to find the slope at this flat point right here, if I took it between these 2 points, I'm not going to get a very accurate representation of the slope over here because these points are way too far apart. But as I pick points that are closer to this line starts to bend down and gets much closer to modeling the correct curve at this single point. If you can get the secant line to touch the graph at a single point, it becomes a tangent line, and the slope of this line is accurate to the instantaneous rate of change of that point on the graph, meaning that our goal is to figure out the tangent line by getting really close with the slopes of our secant lines. So here's our challenge. We've got a graph here of the function 3/4 times x squared, so x squared with a dilation of 3/4. And we want to find the slope of the tangent line at x equals 3, or whatever the instantaneous rate of change is at x equals 3. So to do that, we'll take some slopes of points that are close to x equals 3 in comparison to it, and we'll see if we can figure out a pattern that leads us to an answer. If we want to find the slopes at any of these points, we'll need to plug the points into this equation here and complete it. Note that these up here are basically y values and these are x values, so you've got a change in y and a change in x. That's why this is our slope right here. But you can see if we do the slope formula here, we're going to get a numerator of -15/4 and a denominator of -1, and that comes out to just 15/4 or 3.75. So we can say that that is the slope for the line between 2 and 3 for this function. Now, this is a pretty good slope, but this is not going to be the most accurate thing that we can get, and we can kind of visualize that if we actually try to draw a line between these points from 2 to 3. We can see that the line gets close, but especially if we zoom in here, you can see that we're not quite hitting the curve perfectly. We're still missing parts of it, so we could probably have a more accurate answer with some closer points, especially if we tracked out a bunch of them and then tried to establish some sort of pattern. So I think that's going to be our next goal, is to complete this table by figuring out all of the different slopes between 2 and 3. Now, I don't really know about you, but I know how to do a slope. I know how to plug in some y values, do a subtraction, and do a division. I certainly don't want to do that like 10 times in a row, especially with a bunch of decimals in order to figure out this table. So I put together a Desmos program that'll make getting the slopes for a bunch of these points a lot easier. For starters, we're just going to enter the equation that we have for this, which is 3/4 x squared. And then we're going to enter our anchor point here, or the point that we're trying to find the slope for. In this case, that is x equals 3. Now, if I want to get a bunch of slopes, I can just add those points to this table here. So I'm just going to take the same x values from the problem, and I'm going to put them into this table, and all of my slopes will show up over here. Basically just doing all the calculation for me, so I don't have to bore myself with it. So here's the 3.75 that we got in the first place, and you can see as we get closer to 9, this has actually gotten all the way up past 4, so maybe we weren't that accurate over here in the first place. But I'm also noticing the space in which this is increasing seems to be maybe slowing down a little bit. So as we move closer here, I'm noticing that we're not even really being able to get past 4.4. It looks like we've got 4.2, 4.6, 4.8, and 4.9. I bet if I added some more 9s onto this, we maybe would hit a ceiling here. Alright, this is starting to look a little bit more obvious. We can't actually put 3 into this because we will get an undefined answer, but it looks like if we could actually get a slope here, it's probably 4.5. That means that we can put this in as our answer for the problem using it as a limit statement, or basically the limit as x approaches this value for the slope, we are going to get 4.5 as an answer. That's our slope of the tangent line. So going back to the problem then, here is our completed table, and here is our completed limit statement. The limit as x approaches 3 from the left, because we did come from behind 3 all the way up to it, is 4.5. If we come from the right side of the point by basically looking at values from x equals 4 and moving backwards to 3, we can see we get the same type of result where the slopes are initially bigger than 4.5, but as you get closer to the actual value, this starts to become very clearly 4.5 if we round it off. This means that we can also say the limit as we approach the slopes from the right is 4.5, and since the limits from the left and the right agree, our true limit is also 4.5, making this the slope of the tangent line. We can talk more about exactly what this means in the next lesson because it's sort of a lot to absorb, but for now, I really want to encourage people to try to use the Desmos file to complete these tables of slopes, unless you want to do a bunch of slopes by hand for each of these problems. It might be really annoying, but it's up to you. Anyways, give these a try and we'll see what we can do from here. Thanks. See you soon.